Hey guys, this will be 7.3 and 7.4. At this point, you guys have probably already got the homework assignment and you're like, oh my gosh, there's 6 pages. Yeah, but there's one problem for each page. So there's only 6 questions. The only reason why it takes up 6 pages is because they give these massive images of what we call slope fields, which is what 7.3 and 7.4 is about. And so slope fields are supposed to give us a solution to a differential equation. So given a differential equation, given a differential equation like dy dx is equal to something, remember that its solution is found by finding, antiderivatives. But whenever you find antiderivatives, there's always that plus c, which means the solution to a differential equation is a family of functions. And so that's what a slope field does. It kind of gives us a weird kind of visual where we can actually see infinite or mini solutions. So for whatever slope field, so there is a differential equation for this slope field, and the differential equation might be in the form of dy dx is equal to something 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 in terms of y and in terms of x, or it might be just in terms of x, or it might be just in terms of y. Whatever the differential equation is, it's produce this slope field where this curve right here, so if we follow along right here, we get something like this. This curve right here is a solution to this one, or it might look something more like that right there. So that solution is also, that curve is also a solution here. You might get something down here. This is also a solution. So infinite mini. And then these little lines that you see right here are just small little tangent lines that are going to be on the curve. And so that's what those are. They're representing small tangent lines that should give us a rough idea of what the slope is going to be for what the shape and slope is going to be of the curve at that point right there. So slope field for a certain differential equation is shown above. Which of the following statements about the solution to the differential equation must be false? So I'm going to mark that here before I forget, because sometimes I forget that what I'm looking for is false, not true. The graph of the particular solution that satisfies f of 1 of negative 1 is concave down. So let's go ahead and check here. So we got 1, negative 1. Let me do my best to kind of get that point right there. So that might be like right here. So this is a point on the curve, and it looks like if I follow this right here, it's kind of hard to see all the points, but if you follow these little tangent lines, sometimes you can get an idea of what it's supposed to look like. So let's say that this was the particular solution, meaning this is a particular solution. All of these curves are infinitely mini solution, but let's say that we have a point on the curve that gives us a particular solution. Is this curve concave down on the interval from 0 to 2? And it sure looks like that to me. So I'm going to say that this is a true statement. I think that this is true. Okay, the graph of the particular solution satisfies negative 1, 1. So if I go to negative 1 and move on up to 1, so I think that puts it like right there. So kind of trying to gauge where it might be, depending on the flow, I guess you can say, the flow of these tangent lines. I'm guessing it kind of looks something like that. And it's going to be concave up on the interval from negative 1 to 0, and it does seem like that's going to be true. So I'm going to say that that's true. The graph of the particular solution satisfies the point 0, 0. So we just have a point here. It's concave up on the interval from negative 1 to 1. So let's see if we can graph this. So it looks like around here, the flow of the the slope field is that the derivative is 0, flat right here, but it does seem like it kind of curves down in this direction and curves up in that direction. So roughly I would say that it might look like this right here. So if we're considering negative 1 to 1, it looks like here it's concave up, but it looks like here it's concave down. I think that the curve that passes through the point 0, 0 on the slope field is going to be both concave up and concave down on the interval from negative 1 to 1. So I think that this is false right here. But let's check this last one. The graph, so 0, 0 has a point of inflection. Okay, well that would be true here. That's what it looks like. So here I said it was concave up, and here I said it's concave down, which would make that a point of inflection. So I think that would be true. I'm going to go with C on this one right here. Okay. Let's try 2. The slope field of a certain differential equation is shown above. Which of the following could be the particular solution to the differential equation of 0, 0? So 0, 0 right here, it looks to me, just following the flow that's going through there, might look something like that so far. Okay. Negative cosine of x plus 1. So negative cosine of x plus 1. So let's say we take regular cosine, negative cosine of x. So negative cosine of x would start here and go, wait, that's 1. So it would go like this right here. Plus 1. I think that's going to be the answer, honestly. But let's check these other... e to the x squared minus 1. So if x is 0... If x is 0, the whole thing's going to be 0. Still satisfies our initial condition. I have no idea what x squared, e to the x squared minus 1 looks like, I'm going to be honest. I do not know what that looks like. Let's say I plug in... let's say I plug in 2. So let's just plug in some points. So if I plug in 2, that's going to be e to the 4th. And e to the 4th is actually kind of a large number. Larger than you might think. Not like crazy big, but e to the 4th is 54 minus 1. So that means that at x equals 2, it should have a point that's like way up here. And if that's the case, I would think that these slope fields would be steeper right here. So I'm going to say that that's a no. That one doesn't look right. Sine of x. So does this right here look like sine of x? Well, sine of x starts at 0, 0, yes, but it would look, the slope fields seem wrong because the slope fields would have to follow something like that, which it doesn't. So I'm going to say no to that. Okay, let's look at D. Let's see. So looking at D. Tangent of x. Oh no, tangent of x looks something like that. So the slope field definitely doesn't follow. So I think I was correct in going with this right here. Going with A. Okay. I think that's it for 2. Let's try 3. So for 3, slope field for a certain differential equation is shown above. Which of the following could be a solution with the initial condition 0, 0? So at 0, 0, it looks like the slopes all along here have to be 0. So it looks like it's going, and it looks like there's a vertical tangent or something like at -1 or something. So I actually think that it might look something like this right here. It's going to be 0. And then I think it's going to just like go something like that. Okay. Which of the following could be a solution? I don't know what this graph is, but let's just see if we can use points and stuff. So negative e to the x plus 1. So I don't think that that's going to be an answer, because I see a vertical asymptote, which usually occurs whenever you have a denominator that would make it so this doesn't have any domain restrictions. So I don't think it's going to be A. This is weird. It's got to be C. Sorry, it just took a little bit of a second for me to realize that. So the reason why it has to be C is because of the initial condition. So if I plug in 0, x equals 0 here, I get 1 over negative 1, which would be so if I plug in 0, I get negative 1. So that doesn't fit. That doesn't match with our initial condition. And then for D, does that, if I plug in 0, so it actually could be, could be D. So 1 second. I'm going to get rid of B, though, as an option, because that one doesn't match. But what about, because if I plug in 0 here, tangent of 0 is 0, and I'll get 0 over 1, which is 0. Same thing here. So this matches both of those functions. So let's just see what, how can we narrow this down right here? So both of these have asymptotes at negative 1. Okay, maybe we can plug in just some other points. So let's say I plug in 2. Because if I plug in 2, it looks like it should be somewhere between 1 and 2. So if I plug in 2, I'm going to get 4 over 3. Okay, if I plug in 2 here, I don't know what tangent of 2 is. It's not something nice. Tangent of 2, and then if, so tangent of 2 is about negative 2.185, and then if I plug in 2 here, that's going to be 3. So first thing, it's going to be negative, and it's going to be, so that would be somewhere down here. So it's not going to be D. It's got to be C. Because I think that, so just by plugging in points, I can see that it kind of matches the, where I believe the curve is set to be. If I plug in 3, that's 9 divided by 3, which should be close to 3. So yeah, I feel good about that. And okay, there might be, if you guys look at the key, there might be another better explanation, but I'm just going with plugging in some points for that one. For 4, the slope field for a certain differential equation shown above, which of the following statements about it must be false. So we already did one kind of similar to this. The graph of the particular solution satisfies so negative 3, 2. So negative 3, positive 2. So like probably like right here. Looks like it's a pretty steep slope. Maybe going somewhere like this right here. Okay. Is concave up on the interval from negative 3 to 3. Definitely looks like it. So I'm going to say that that's true. The graph of the particular solution, negative 2, negative 2. So maybe like right here. Something like that, maybe. Has a relative minimum at x equals negative 2. Yeah, there's a minimum there. So I'm going to say that that one should be good. C, the graph of the particular function at 0, 2. So right here. Is concave up on the interval from negative 1 to 3. Yes. Okay. Oh, wait, hold up. 0, -2. My bad. Not 0, 2. 0, -2. 0, -2. I'm going with the flow, so might look something like that right there. Is concave up. Okay, this does not look concave up. Let's check D. The graph of the particular function at 1, 0 is linear. And that could be true. That looks like it's linear right there. So yeah, I'm going to go with C. Because I think it should be concave down on the interval. Wait, check the interval from -1. Yeah, -1 to 3. Yeah. Okay. For 5, the slope field of a certain differential equation is shown above. Which of the following could be a particular solution to this differential equation satisfying 0, 0? Okay, so let's check some things right here. 0 minus 0 is 0, so it does check that. Cosine of 0 is 0. If I plug in 0 here, e to the 0 is 1. 1 minus 1 is 0. Okay, so I think all these fit the initial condition. Let's see what else. X squared minus x. Let's go ahead and draw the curve. So at 0, 0, let's follow the flow right here. Maybe something that looks like this right here. Looks like it's falling to a horizontal asymptote. That looks pretty exponential. If you're asking me, that looks like an e to the negative x minus 1. That looks like a c, if I'm being honest. Now, should I check? That's the question. I feel pretty good about it, since this is a shift down one and there's a horizontal asymptote here, negative, because it's going to, and then you can see that that's going to be a decay. E to the negative x squared, I don't think that's going to be it. Definitely doesn't look like negative sine of x. X squared minus x. So x squared minus x is x times by x minus 1, which would mean that it would have an x-intercept at x equals 0 and an x equals 1. This curve, however, only has an x-intercept at x equals 0, not at 1 for that curve right there. So it's not going to be that one right there. So I feel pretty good about C. And for this last one right here, the slope field for a certain differential equation is shown above. Which of the following could be the solution following this condition? So if I plug in 0 here, natural log of 1 is 0. If I plug in 0 here, that's 1 minus 1. Okay, if I plug in 0 here, that's 0. Alright, so they all fit, dang it. I really kind of like it when we can eliminate some options. So 0, 0. Alright, looks like we have an asymptote at not just x equals 1, but also at y equals negative 1. Okay. Oh man, if we have a vertical asymptote and a horizontal asymptote, that's got to be a rational function. So this definitely doesn't look like a logarithm. Yeah, no, I don't think that's going to be a logarithm. I don't think it's going to be exponential either. It doesn't look like it is. Well, actually, maybe. Hold up. Move to the... That would be down 1. Okay, it might be that. We'll keep that open. Let's see. What are some other things to keep in mind? Some things to keep in mind. All of these have asymptotes at x equals 1. Do all of them have asymptotes at y equals negative 1, though? So so let's think about that. So if there's an asymptote at y equals -1, if you guys go all the way back to chapter 1, the limit as x approaches infinity of our function y has to be equal to -1 then. So what is the limit as x approaches positive or negative infinity? So let's say we do, so this right here is equal to 1 over e to the x squared minus 1. And if we do the limit as x approaches infinity, well, that's going to be negative. Okay, so this is not helping. Sweet. The limit as x approaches infinity here, that is also not going to be too super helpful. Not helpful at all. So all of these seem to match. I don't want to plug in points. It kind of feels like plugging in points is cheating, if I'm being honest with you. But maybe that's what it will take. Let's do that. So, when x equals -1, we should be somewhere like at half. So if I plug in -1 right here, -1 squared, that's going to be about 2 minus 2. That might. I'm running out of options here. So if I plug in -1 here, -1 over 1 minus negative, that's going to be -1/2. Okay, if I plug in -1 here, this is going to be 1. Oh, wait, hold up. Can't be this one right here. Because if I plug in -1, 1 minus -1 squared, that's going to be 1 minus 1. So this one should not work, because this one should also have a vertical asymptote at x equals -1. So, okay, so it has to be between these two right here. So if I plug in -1, e to the -1 squared minus 1, that's going to be e to the -1 minus 1. That's 1 over e minus 1. What is 1 divided by e minus, I don't know what I just typed in. 1 divided by e minus 1 is equal to negative 0.6. I guess that could be close to it, but this right here will be -1/2, and I think that -1 is closer to a half. I really want to say this one. I'm going to go with C. Can't really think of too many other explanations. What about, let's do a limit as x approaches -infinity. So what is the limit as x approaches -infinity of e to the -x squared minus 1? So if this is if this right here is approaching -infinity, okay, that means, well, that's going to be positive, that's going to be negative, that's going to be 0, then all that's going to be 0, it's going to be -1, so it still counts for that. What about as x approaches positive? It shouldn't matter if you approach positive or negative infinity. Positive infinity still going to be e to a negative large number. Yeah. All right, I'm going to call it quits right there. I think it's got to be C. This just kind of screams to me. I don't know why I made it so hard. I don't think this has any vertical asymptotes. So if you plug in 1 right here, yeah, oh, you can plug in 1 right here. Yeah, no, oh my gosh, I can't believe it took me so long. Okay, sorry for that. Hopefully you guys figured it faster than me and you don't have to watch this video. So not going to be B, because this can be equal to 1 right here. But this, our graph should have a vertical asymptote. So that's going to be C. Okay, alright, that finishes up this video.